India may be on the verge of a major breakthrough in missile propulsion technology. The Yantur Ramjet could redefine the future of supersonic weapons, giving India a powerful edge in next-generation warfare. To understand why this matters, we have to look at the physics of flight. Standard rocket systems carry their entire fuel supply on board, but they also have to carry heavy liquid oxygen tanks just to burn that fuel. All that weight severely restricts how far the missile can actually fly. Traditional jet engines, like turbofans or turbojets, solve the oxygen problem by breathing atmospheric air. They use large spinning fan blades at the front to suck in oxygen as they fly. But push those engines past the speed of sound, and the physics break down. At extreme supersonic velocities, the friction and pressure cause those moving turbine blades to literally melt or stall out. The math is simple. To achieve sustained supersonic and hypersonic dominance, engineers cannot simply upgrade legacy engines. They must invent an entirely new method to compress air, one that works without moving parts. For years, India's frontline standard for regional deterrence has been the BrahMos supersonic cruise missile. The airframe, boosters, and control systems are built locally. However, about 15 to 20% of its highly complex subsystems, most notably the liquid ramjet engine itself, are still imported from Russia. Relying on foreign supply chains for the most critical propulsion components limits a nation's strategic autonomy. In a conflict, those dependencies can lead to vulnerabilities that domestic innovation is designed to solve. Before we look at how India is shattering these limits, take a second to subscribe to the Global Warwatch network for more future warfare tech. Enter Paninian, an Indian deep tech startup. They recently unveiled the Yantur Ramjet, an advanced engine designed specifically to power autonomous military platforms. This design removes moving parts entirely, relying on the missile's forward velocity to compress incoming air. Since Mach speed airflow is chaotic, the Yantur solves this using oblique and normal shocks to slow the air, ensuring the fuel ignites cleanly. Looking at this technical diagram of supersonic combustion, we can see how India's state-led DRDO HSTDV program advances this concept. A scramjet allows the air to remain at supersonic speeds even during combustion, a necessity for sustained flight above Mach 6. Weaponizing the atmosphere for compression enables heavier payloads, higher speeds, and extended ranges that once felt out of reach. Generating propulsion at Mach speeds creates immense friction. This subjects the engine materials to devastating thermal loads that can burn right through the hull. To survive this, Paninian engineered the Yantur using advanced high-temperature materials and specialized protective coatings, rated to withstand thermal extremes of 2400 Kelvin. Their secondary defense is active cooling. Using a thermal oxidant fuel system, the missile pumps its own unburned fuel around the outside of the combustion chamber. This liquid absorbs the heat before it is injected into the center to burn. Heat is only half the battle. High-speed experimental engines frequently shatter due to thermal-acoustic instability, violent vibrations caused by the intense pressure of supersonic flight. To counter these waves, Paninian developed a digital solution. An adaptive fuel control system dynamically recalculates the fuel injection in real time as the missile changes Mach speeds, smoothing out those dangerous vibrations. Survival at these speeds merges specialized metallurgy with a constant balancing act between thermodynamic physics and real-time artificial intelligence. The Yantur Ramjet functions as a modular core designed to integrate directly into an expanding web of autonomous platforms. This is the heart of the Svayat L1, a long-range, land-attacked cruise missile. It uses terrain-hugging flight profiles and AI-driven navigation to penetrate heavily defended airspace with minimal detection. Beyond cruise missiles, this modularity extends to high-fidelity target decoy drones and collaborative combat aerial vehicles, also known as loyal wingmen. This private sector engineering complements ongoing state efforts, such as the DRDO's solid-fuel ducted ramjet, which is being tested to power future long-range air-to-air missiles. By integrating domestic deep tech startups and replacing complex foreign subsystems, India is pushing its missile programs toward 95% indigenous content. It marks a transition from a dependent importer to a sovereign power with absolute conventional prompt strike capabilities. Thank you, everyone, for your time and participation. Please like, share, and subscribe to Global Warwatch Network. Share your thoughts on this propulsion breakthrough in the comment section, and join us on social media. The links are provided in the description.